Exercise 721 is asking you to draw the complete mechanism for some SN1 reactions. Now, we saw in the last few videos how, in addition to the two essential steps in every substitution, loss of a leaving group and nucleophilic attack, SN1 reactions can have some extra steps. You could have a carbocation rearrangement, you could have a proton transfer at the beginning, and you could have a proton transfer at the end. And we've spent some time in the last few videos recognizing when each of those would happen. So those previous problems are just going to be the first step in this problem. The first step here is to figure out which of these steps you would want to know this sort of flow chart by heart. And the first step is to figure out which of these steps we are going to have to draw in this mechanism. So let's do this one at a time. Will we have a proton transfer in the beginning? Well, what type of a leaving group do we have? The leaving group is right here. That leaving group is a bad leaving group. We've seen it before. If that leaves, takes the electrons and goes, it's an OH-, which is very unstable by itself. So we're going to have to turn that into a better leaving group by doing a proton transfer. So we will need this first step. You always have to show loss of a leaving group. Now let's think about carbocation rearrangement. Remember, you replace the leaving group with a carbocation. So imagine if our leaving group here were instead a carbocation. That would be a tertiary carbocation. This would be primary, secondary, and secondary. So tertiary is the most stable, so we don't have to worry about carbocation rearrangements. The carbocation will already be on the most stable carbon. So we don't have to worry about drawing a carbocation rearrangement. You always draw a nucleophilic attack. That's always part of a substitution reaction. And then let's look at the proton transfer. Now if you look at this, it does seem, these definitely are two nonmetals, so it does seem like those are, like that would not have a charge overall. But the truth is that that when you put this into solution, this is a strong acid. The H and the Br separate, so the H becomes an H+, there's the acid, and the Br becomes Br-. In fact, all of the halogen acids except for HF are strong acids, so chlorine, bromine, and iodine. If you combine those with hydrogen, those are strong acids. HCl, that's stomach acid, HBr, HI, those are all strong acids. And they're strong acids for the same reason that the halogens are good leaving groups. They're able to take the electrons and go their own way. So they leave the hydrogen all by itself with a positive charge. So although those are not salts, they're not ionic compounds per se, they are strong acids, so they dissociate, and your nucleophile does end up having that full negative charge. So because the nucleophile has a full negative charge, we are not going to need to do that proton transfer at the end. So here the mechanism will just have three steps: a proton transfer at the beginning, loss of a leaving group, and nucleophilic attack. Okay, so let's start. We have this cyclohexane, and it has a methyl group and this OH. So that's a bad leaving group, and we need to react it with some acid in order to put a hydrogen here and make it a better leaving group. Luckily, we have this acid here. So you could imagine this H and this Br, they're held together very weakly. It's a strong acid, they break apart very easily. Certainly, the bromine is more electronegative, pulls the electrons to itself, and the hydrogen is slightly positive. Similarly, the hydrogen here is slightly positive, and the oxygen is slightly negative. So to do the proton transfer, to turn this into a better leaving group, the slightly negative oxygen steals the hydrogen from the HBr. Hydrogen can only form one bond, so if it's going to form a new bond, the bond it has to break, and those electrons go on to the bromine. So that's our proton transfer. Okay, so after the proton transfer, what we have is an awesome leaving group. And we also have the Br minus. Okay, so this is an awesome leaving group. It's water. If that comes off, water is very stable. And so now that we have a good leaving group, we can do the loss of leaving group. That can take those electrons in the bond and just put them on the oxygen. This is our loss of a leaving group step. And in that case, there we go. So in that case, after that step, we end up with a carbocation. So we just have the methyl group. Where the leaving group left, we have a positive charge. And we do also have that water there floating around. Now notice, we're following the story of this carbon chain. This organic chemistry, we're focusing on this carbon chain. The rest of these things are there. They're floating around. This Br minus is floating around. The water is floating around. But unless it's relevant to the behavior of the carbon chain, we don't really focus on it. It's irrelevant information for our story, which is the story of the carbon compound. So we already saw how we don't have carbocation rearrangement here, because we have a tertiary carbocation, and any of the other positions would either be primary, secondary, or secondary. Any of the adjacent carbons. So that carbocation is already as stable as it's going to be, and what ends up happening is this bromine comes back as the nucleophile. And so that swoops in and attacks, here let me actually, swoops in and attacks that positive electrophile. So this is our nucleophilic attack. And that leaves us with our product. Now notice that here we don't have a chiral center, because going around the ring one way is the same as going around it the other way. You run into the same stuff at the same point. So it's not a chiral center, but because this is an SN1 reaction, if it were a chiral center, we would get both enantiomers. Remember that this carbocation intermediate is flat. It's trigonal planar. It's like a pancake. And so then the nucleophile can attack either from the top, giving you one enantiomer, or from the bottom, giving you the other enantiomer. So when you do an SN1 reaction on a chiral center, you always get two products, the two enantiomers. But since there's no chiral center here, we don't have to worry about that. And so that's the full mechanism for this SN1 process. You do a proton transfer, followed by loss of a leaving group, and then nucleophilic attack. And we're done. Okay, let's try B. And before we get started here, we'll just put some extra room to write. Okay, the first step is the same as before. We want to see which of these steps we have to do. This way we won't miss out on anything, we won't forget anything. We'll just have a clear idea of what we need to include. So let's look for our leaving group. Our leaving group is right here, and that OH is a bad leaving group. We saw it in the last example. If that picks up its electrons and tries to leave, it ends up forming a hydroxide ion, which has a full negative charge on a relatively small atom, oxygen. So that's pretty unstable, and that'll just be attracted right back to the carbocation, and it won't float away. So that's a poor leaving group. In order to make this substitution reaction happen, we have to put a hydrogen on there to turn it into a better leaving group. So we will have to do this proton transfer because we have a bad leaving group. You always have to do loss of a leaving group. I'm sorry, you always have to do loss of a leaving group. And then with carbocation rearrangement, take the leaving group off and imagine that a carbocation was there in its place. And then ask yourself, is that the most stable carbocation compared to each of the carbons that's adjacent? Now this is a secondary carbocation because this is bonded to 2 carbons. Next door is also a secondary carbocation. That carbon is bonded to 2 carbons, or that would be a secondary carbocation. So there's no reason for it to go there. But to the right, this is bonded to 1, 2, 3 carbons. So if the carbocation went there, it would be more stable. It would be tertiary. So because there's a more stable place nearby, we will have this carbocation rearrangement. Okay, we'll revisit that when we draw the mechanism. You always have nucleophilic attack. And let's think about this proton transfer. We have HBr, one of those strong halo acids. So this effectively acts like H+ and Br-, because the 2 species split up very quickly when you put them into solution, because bromine is such an amazing leaving group, it'll just leave the hydrogen behind. So we effectively have a nucleophile with a full positive charge, so we don't have to worry about drawing this last proton transfer. We'll just have the first 4 steps. Okay, so let's try to draw those. So we have our cyclopentane ring. We have a methyl group going away from us, and this hydroxyl group coming out at us. Okay, well that's our bad leaving group. The first step we have to consider is this proton transfer. We have to put a hydrogen onto that molecule, onto that OH, in order to make it a better leaving group. And luckily, we have an acid already in the solution. The bromine is slightly negative, it's pulling electrons to itself. The hydrogen is slightly positive. It's losing its electrons to bromine. Similarly, this hydrogen is slightly positive and the oxygen is slightly negative. So the oxygen steals this slightly positive hydrogen. The hydrogen can only form 1 bond, so the bond it already has, those electrons go onto the more electronegative atom. And there we have our proton transfer. So once you do the proton transfer, we will be left with this lone pair turning into another bond to a hydrogen. And this oxygen now will have a full positive charge. It's a formal charge, but it's an awesome leaving group. In addition to that, we will have this Br- floating through the solution, and we'll only ever consider it again if it becomes relevant to the carbon chain that we're following. So that's a proton transfer. Next step is loss of a leaving group. So our leaving group now is an awesome leaving group. It's this, which is water. If that comes off of the molecule, pops off of the molecule, then it's water. And so we have, and so it'll be stable, so it will leave the molecule behind. So we'll have water off of the ring. That's this. And then it took its electrons with it, so now we have this carbocation where it left. Okay, and we saw before that we do have a carbocation rearrangement. So that's our next step, drawing that. So the reason why we have this carbocation rearrangement is because this is a secondary carbocation, but the carbon right next door is bonded to 1, 2, 3 other carbons. That is tertiary. So if the carbocation were to move over there, it would be more stable. Now note that there is a hydrogen. The hydrogen is coming out at us. It's a tetrahedral carbon. It already has 2 bonds in the plane and 1 going away. Notice that this is a methyl group. Nothing is written at the end of that dashed wedge, so it's a CH3. And you would never, ever draw the curved arrow showing the movement of the positive charge. Curved arrows show the movement of electrons. And the way that you get these carbocation rearrangements is that you get a shift. The smallest group at the more stable position moves over. And that can either be a hydrogen if it's there, or if it's not there, a methyl group. There is a hydrogen here, and so that takes up its electrons and moves over. That's the mechanism for the carbocation rearrangement. So once you have that carbocation rearrangement, you end up with this here. So you have your hydrogen moved over, and now you have your methyl group. And notice how I'm drawing it. It was going away here, but now it is in the plane because it's a this is a carbocation, and the carbocations are trigonal planar. They're flat. So all of these three bonds are going to be in one plane. Okay, well that is our carbocation rearrangement, and then the last thing we have to worry about is nucleophilic attack. So the nucleophile, and if you are ever in doubt, you could look at what was added in the exercise that they give us. But the nucleophile is this bromine. It's just a strong nucleophile. So that is a full negative charge. It's going to attack that positive charge. And the bromine here swoops in and attacks that electrophile. So that's your nucleophilic attack. So we will have our cyclopentane ring, our methyl group, and the bromine. Now notice that this is not a chiral center. Going around the ring one way, you hit the same things at the same point as going around the other way. So in each direction, that ring is the same thing, bonded twice to that carbon. So it's not a chiral center, and so you don't have to give the three-dimensional arrangement. Sure, two of these bonds will be in the plane, one will be coming out and one going away, but it kind of doesn't matter which is which because it's not a chiral center anyway, so they all amount to the same molecule. And so the mechanism for this, one step at a time, is first the proton transfer. So the way we solved this was we took our flow chart, we saw which steps we had to consider, and then we drew them one at a time. We did proton transfer, followed by loss of a leaving group, followed by the carbocation rearrangement, and then nucleophilic attack. All right, let's try that with another one. So the first step here is going to be just figuring out which of these steps in an SN1 mechanism are going to be relevant to this exercise here. Okay, well, first step, let's look at our leaving group. Our leaving group is a bromine, which is an awesome leaving group. The halogens are great leaving groups. They're very big atoms. They can take electrons with them and spread them out over their enormous space. And that dilutes their charge and that stabilizes them. So they're very stable anions. They're very stable negatively charged ions. And so they're great leaving groups. So we have a good leaving group, and so we don't have to worry about doing this proton transfer in the beginning. You always will do a loss of a leaving group. That's just part of a substitution reaction. Let's think about whether we'll have a carbocation rearrangement. To figure that out, replace the leaving group with a carbocation. Wherever the leaving group is, it's going to leave and leave behind a positive charge. That carbocation is tertiary. Next door, it's either primary, or tertiary. So it's already on a position that, the most stable position that it could be. It's already on a tertiary carbocation, and at most, there's a tertiary carbocation nearby. But why go through the trouble? There's an energy barrier to move a hydrogen over. Why would that happen? Just to produce the same amount of stability. And so we will not have a carbocation rearrangement, because the carbocation is already on the most stable position. So we don't have to worry about that. We'll always have nucleophilic attack. And now, how about the proton transfer at the end? Let's take a look at our nucleophile. Our nucleophile is water, completely covalent, has no full negative charge. Well, when the nucleophile has no full negative charge, that's when you have to do this proton transfer. And so we will have to do that proton transfer at the end. Okay, so now we have a clear idea of the steps we need to include. And so first we'll start by drawing the molecule. And our first step is loss of a leaving group. So the leaving group is bromine, takes the electrons, pops off the molecule. Now that bromine already has 3 lone pairs, so when it pops off of the molecule, it will leave a carbocation behind, and you'll have that bromine now floating around in solution, and we'll only consider it again if it affects the carbon ring whose story we're following. We saw that we don't have a carbocation rearrangement, so the next step is going to be nucleophilic attack. So with nucleophilic attack, we take our nucleophile, and here our nucleophile is water. So we take our nucleophile, and the oxygen there has lone pairs, which are nucleophilic, and it also has a slightly negative charge, which makes it nucleophilic. It's getting that charge by stealing electrons from the hydrogens, which then becomes slightly positive. So it uses that's acting as the nucleophile, and it attacks the electrophile. So that's our nucleophilic attack. Now once it goes onto the electrophile, it is sharing a lot of electrons, and so now the oxygen has a positive charge. So that's unstable, and that is why we have this proton transfer at the end. So that is the next step that we need to do, the proton transfer. And there are several different things you can use here. You can use another water molecule, or we could bring this bromine back if it's relevant to the carbon story. This bromine you could imagine that stealing one of these hydrogens back, and the electrons would go onto the oxygen. We're using a bromine here. We could have also used a water molecule. Honestly, it would probably be a water molecule because this is too good of a leaving group to do this, but most of the time. But it's fine if you want to use the structure that was in your mechanism. And so we end up with that, which is our product. That was the product that we wanted. So our first step was to look at which features of this flowchart are relevant to this equation, and then one by one go through them. First, loss of a leaving group, then nucleophilic attack, and finally proton transfer. So to avoid making these videos unnecessarily long, I'm going to stop this one here, and we'll pick up with D